All right, now we're going to look at some common structures. So again, review. Sediments generally get deposited horizontally. And if you then erode those deposited sediments, you'll get a mesa. We have a lot of mesas around here because a lot of San Diego has not tilted substantially since the sediments that we see around have been uplifted. But we do see a good deal of uplift, and so we have all these sort of flat-top mesas. When you do coastal geology, we'll explain a little bit more what's actually happening there, but this is a good start. Gone over strike and dip, but this certainly will help you understand it a wee bit better. Look at this diagram. Here again is our line of strike. And which way do you think that dip is? Hopefully you are pointing that way. So, question 2. How many bed orientations do you see in this outcrop? A very famous outcrop. If you pick E, I would love to go to a rock concert with you, but that's about all. I see at least 2. I've heard people say they see 3 in there. You sound like fun if you see more. If you see more than 3, but yeah. So a couple expressions of dip, just to review. You got your hogbacks. This is Front Range, Colorado, near Boulder. Locally, in San Diego, we have these cuestas. These sort of these are really, really tiny flat irons. And of course, once again, our mesas. This is pretty much horizontal sedimentary rock, and yeah. So now we're going to go back to what we did during our earthquakes lecture and take a closer look at stress and strain. We have our elastic deformation, our brittle deformation, and generally the first thing you see in deformation is something we call jointing. So what we saw in the picture was jointing. Cracking with very little visible offsets. Moved between the cracks, but you're definitely seeing the cracks, and they may not seem like a lot, but when you have thousands and thousands of tiny cracks that are maybe fractions of a millimeter, it adds up and can be a very effective way of relieving stress. I mean, this is usually the first thing we see when rocks are deforming brittly, and all rocks pretty much probably have some degree of jointing. The question is just how much. There we go. And so we see a lot of this, for example, out east along I-8. This is a shot from Inkopog Gorge near Desert Tower. Here's some from Mission Trails, and these are not actually layers in the rock. What you're looking at is some places where there's recent high water marks. They left some mud on the side of the rock. Not sure what the heck happened here, but clearly there's something wonky with this file. Now, the second class of deformation is going to be ductile deformation. This is a soft deformation where the solid behaves in a more fluid fashion. And so you generally see one or the other or some combination of these in all rock that has undergone some kind of stress. Generally, brittle deformation will take place towards the upper parts of the crust. However, you can get ductile deformation in soft, unconsolidated sediments near the surface. Great examples of this include places around the Los Angeles basin. Otherwise, most of your ductile deformation is going to be taking place probably deeper down in the crust where the heat has started to make the rocks behave a little bit more plastic. So now we're going to focus on different types of brittle deformation. Deformation where there's actual offset. We're going to introduce our next term, fault, with offsets. We're going to take a tour on a couple different ways the faults might express themselves and what they might look like in their natural environment. So the first fault we're going to look at is what we call faults where the predominant direction of slip is along the dip of the fault plane. We call these dip, slip, faults. They come in two classes. And first class is what we're going to call a normal fault. And before we define the normal fault, I want to take a close look at this plane here. And what you'll see is you have a top of the fault. There's one fault that kind of overhangs the other. We call this overhanging side of the fault, we call it the hanging wall. We call this side down here the footwall. So in a normal fault, the footwall moves up, the hanging wall moves downward, and you end up getting horizontal extension. They may wonder, wait, why do I have these two arrows pointing towards each other? That is because we have because in all parts of the Earth, there's always compressional stress. It's just that in a normal fault, you have greater compressional stress vertically than you do horizontally. And so things are going to expand in the direction of stress, as we learned from our metamorphic rocks. If the greatest stress is in the horizontal direction, you're going to get a different kind of fault. You're going to get a reverse fault. Now, everything comes closer horizontally. Notice how strong pad and the cheat have come closer to each other compared to the previous. And notice how the layers here have thickened. If you're to drill down, you would see this blue layer repeat and white layer repeat themselves twice in your drill core, indicating that you have a reverse fault. Now, another name these go by, we see a lot of these on the north side of the LA basin. This is what gives us the big mountains where we have places like Big Bear Lake, are thrust faults. But the more broad terminology is reverse faults. So now we're going to look at faults where the direction of slip is horizontal. These are what we call strike slip faults. First of these is your right lateral strike slip fault. So looking back and forth here, you can see that the cheat has moved horizontally to the right with respect to strong bad. So if you're standing here, looks like everything on the other side of the fault has moved to the right. A lot of people ask, well, wait a minute, what happens if you're standing on the other side of the fault? What has happened? Same thing. Everything appears to have moved to the right. It's that whole sort of perspective thing that you see me struggling with these videos. Classic examples is the San Andreas, where you have, if you can see, all these creeks have shifted to the right. Or in this picture I took near Palm Desert, all the creeks have shifted to the right. This is contrast with the movie San Andreas, where does this look like this is shifted to the right? Seriously, you had one job! One job! I could probably make an entire YouTube video about what is wrong with this movie. But what cheeses me off beyond all recognition is this. This is the thing that infuriates me about this movie the most, is that they portrayed the San Andreas fault as a left lateral fault when everyone knows that this is a right lateral fault. Not only that, this chasm is not going to happen. This is, this would be a left lateral fault. In a left lateral fault, everything appears to have moved to the left. Doesn't matter which side of the fault, everything's moved to the left. Here we're looking at Lebanon, everything's moved to the left. There we go. All right, wrapping up. Yes, split. Sorry, I'll get out of your hair. I'm trying to